Okay, so continuing with this lecture on generating simulated data for within subjects designs. We've reached the point where we can produce data with varying intercepts and slopes specifications, right? And so once we have generated such simulated data, we can fit the same model as M3 that I'd shown you earlier with varying intercepts and slopes with no correlation between the intercepts and slopes, right? But this time we have a parameter specifying the true value of the slope adjustment standard deviation, right? So what we will do is we will repeatedly generate simulated data. Then we will fit the model with varying intercepts and slopes, no correlation, so the double vertical bar, and then print out the summary from the model and check whether the model parameters roughly match the true numbers that you use to generate the data. That's the sanity check, checking whether parameter recovery happens or not under repeated sampling. But we can also use this for doing power calculations now. Okay, so this is getting closer to the true way, the correct way to do power calculations. Okay, we're getting closer and closer now. So what I want you to do now is to write a function called gendat that generates data, which takes as input the sample size for each subject, the number of replicates, the intercept and slope fixed values, and the three variance components for the intercept, slope, and the standard deviation. So you just write a function that will produce simulated data using the code that I've shown you earlier. Okay, so you just have to assemble the code now from the little pieces that I've shown you, and the output should be like this. Like when you give it some values like 5 subjects, 5 replicates, some values for these, and you should get simulated data that looks like this now, right? There'll be a subject column, condition column, and RT column. So notice that I didn't give any condition values here. That should be inside the function just for the 2 condition case right now. This is not a very general function. It's just for the 2 condition case, right? Okay, so once you have written such a gendat function, you should write a for loop with, let's say, 100 iterations that computes the proportion of times that the absolute value of the t-score for the slope is greater than, let's say, 2, right? Just take that as a critical value. So this is going to be the estimated power of the experiment approximately, and this would be the probability of detecting the effect given that it's true, right? So the true effect is 25 milliseconds, or rather actually 50 milliseconds. The slope is 25 milliseconds in the plus minus 1 coding. So the proportion of times that we would detect that significant effect will be the power, right? So that's something you should do. Okay, give it a shot, because I've shown you all the little pieces that you need to do all this, but you can now write this for loop. And what I say here is that you should use the, sorry, did I say t-test? I did not mean t-test. I said this t-score for the slope from the linear mix model is what you should use in this case to check whether you get a significant effect or not, right? So because we have completely balanced data, the t-test score from the linear mix model will be exactly identical to the result that you get from the ANOVA. That's why we can just use the t-test score here. In general, I would recommend that you use the ANOVA function in case you have imbalance in your data when you're doing data analysis. But in this simulation code, the simulated data is perfectly balanced. There's absolutely no missing data at all. So therefore, it's fine to use the t-test value from the linear mix model to compute the power. Okay, so that's what you should try out. And the next topic that I will cover now is how to generate data with correlated intercepts and slopes. Okay, so the way we will generate correlated data is that we will have to use the bivariate distribution, right, which I have discussed already in the course. So the way we will do this is that we will use a library mass and generate a variance covariance matrix and use that variance covariance matrix and the multivariate R norm distribution from the mass library to generate certain number of subjects data. So in this case 50 subjects data, such that the intercepts and slopes are both coming from a normal distribution with mean 0, and the variance covariance matrix determines the standard deviation between standard deviation of the intercepts and the slopes, right? So the standard deviation of the intercept is 200 and that of the slope is 50, and some correlation, and that correlation is defined in the off diagonals as 0.5 here. I've just taken 0.5 as an example. So this MVR norm function is going to generate bivariate data now, right? That will be correlated. We will have correlation 0.5. Okay. So how does this work? I can look at, so when I generate this bivariate data and save it in this matrix U, what I'm getting is 50 rows, and the first column is the intercept adjustments and the second column is the slope adjustments, right? And the correlation 0.5 you can visualize by plotting this pairwise in a plot, right? So this is the U0 matrix, this is the U1, sorry, the U0 vector, the U1 vector, and you can see a positive correlation here which is about 0.5. If I had set this correlation to 0.9, I would get an even tighter correlation here. Okay, maybe I should do this. Let me just do this now. Oh no, sorry, this is here, right? Right, so here it is. I have my library. So I've generated this correlation, this matrix here. If I look at the plot, I see that the, I should redo this. Right, so we see this positive correlation here. It's pretty noisy, but you can still see it. But if I change this to 0.9, right, much higher correlation here, what's going to happen is that if I look at the correlation plot again, I'll see a much tighter correlation here, right? So this correlation parameter actually is being specified by us as the gold standard parameter, you know, that we are using for generating the simulated data, right? Just like we used the standard deviations of 300 for the sigma, 200 for the intercept, and 50 for the slope, we are adding one more parameter, which is the correlation, and we are specifying what that correlation is going to be for generating simulated data. All right, so if you had assumed that the correlation was minus 0.5, right, then you would write minus 0.5 here, and then you would get negative correlation here. Okay. All right, so, and if you specified the correlation to be 0, then you could generate exactly the same type of data as we generated with the double bar syntax earlier, where we had two independent intercept and slope generations of for each subject using the R norm function, right? So this MVR norm function can generate the same type of data as the two independent R norm functions if you set the correlation to 0. Okay, it's an important point. And so if the correlation is 0, now you will see basically no association between the intercept and slope anymore. You can't really see this very well here. Look, there's a lot of variability, and that's because we have very sparse data here. We have only 50 subjects data, I think, right? 50 data points. Okay. So what I just showed you is the way that you can generate correlated intercepts and slopes using the MVR norm function. And so what you now need to do is you need to extend your GenDat function to generate correlated intercepts and slopes by using this code that I've shown you, right? You're going to have to define a variance covariance matrix that has So let me show you what this looks like. Right, so if you look at the sigma here, so let's just, if you look at the variance covariance matrix here, what we have is on the diagonals you have the variances, that means the sigma squared for the intercept adjustment and the slope adjustment. Okay, on the off diagonal you have something called the covariance, which is the two standard deviations for the intercept and the slope multiplied with the correlation. That is the definition of covariance. Okay, and so on both the off diagonals you are seeing the covariance here, right? The two standard deviations, intercept and slope standard deviations multiplied with the correlation gives you the covariance, and that's this value here. So this is this matrix, this variance covariance matrix is what goes into the generation of bivariate data, right, that has some correlation with each other. That's just how multivariate data is generated. Okay, right, so you should now be able to extend your gendat function to generate correlated intercept and slopes, right, and then compute power using this function, right, and then you can check whether the parameters are recovered under repeated sampling and so on, right. So all this will be part of the homework assignment for you. So I will give you some practice in doing this, and I will help you in producing this code step by step, okay, in the homework assignment. So that's it. That's the whole lecture on generating simulated data. What is missing right now is generating more realistic data in the Latin square design. Right? That is something I will talk about in the next week's lecture. We are now at the point where we can generate reasonably realistic repeated measures data, and we can compute power with it, but we are still short of the final step where we can produce Latin square designs. Okay, but we will come to that later after we've had some practice with this setup that I have taught you. So that's it for this lecture then on simulation, at least for this week.